So last week we covered vector fields, and we started talking about line integrals, and we did line integrals of scalar functions and line integrals over vector fields, and just kind of cover this new concept where basically instead of trying to evaluate the value of a function over an area or over a volume, we're now trying to evaluate functions over paths. And in 2D, those are 2D little flat paths. They're little lines that kind of squiggle around like this. And in 3D, they might look something like this if we were integrating and trying to calculate a line integral over some path of a fly kind of just buzzing around in 3D space. And I gave examples of why we might care to do this. We also talked about a special type of vector field, which we called a conservative vector field. And a conservative vector field has the kind of interesting property that it is the gradient. It is the gradient vector field for some potential function f. Okay, and so we'll write that down. That the vector field f, and it could be it could be a 2D vector field, it could be a 3D vector field, whatever. If this can be shown to be the gradient of some scalar function, then we're set. We have a conservative vector field. And I claimed that it would be kind of useful for us to know when we're dealing with conservative vector fields, and now is the time when we start to touch on that topic. So if you'll remember back in Calculus 2, when we first learned about integrals, we had this thing which we called the fundamental theorem of calculus. And the fundamental theorem of calculus took us from doing problems like this and x squared dx, and where we would just evaluate this to be x cubed over 3 plus c, and said, look, if we're evaluating this integral over a specific region, like say from 1 to 4, x squared dx, how do we do this? Do we have to do infinitely many additions of these little rectangles and stuff like that to get the answer? Do we have to do a lot of hard math? And it turned out that the answer was no, that we could simply evaluate and get x cubed over 3, and all we had to do was evaluate this at the endpoint. Somehow, some way, right? The math was that we just plugged in the endpoints, right? We plugged in 4, and we plugged in 1, and we evaluated this, and we would get 63 over 3, and this would be the answer for this particular integral. And this was the fundamental theorem of calculus. So fundamental theorem of calculus, that was this. And it turns out there is an analogous property in multivariable calculus for line integrals. Now, it comes with a couple small caveats, and I would strongly suggest checking out the textbook because you cannot always use this tool, but when you can use it, it proves to be extremely useful. So I am simply going to write down the theorem. Okay, it is the theorem. It is the fundamental theorem of line integrals. And so here it is. So I'm going to write some stuff down, talk about some little caveats of it, and then we're going to do an example that kind of shows its use. Okay, so let's let C be a nice smooth curve. Okay, and I'll explain exactly what that means in a moment. Given by the vector function, just like we always have. We're going to call it R, the vector function, the path function, R of t. Okay, and let's let A just be some values between A and B. It could include the endpoints or not, doesn't matter. Okay, and then let's let f of x or f of xy, and this extends into 3D, but we'll just write it for 2D, be differentiable, whose gradient vector, is continuous. Is continuous all along this path. Continuous on C. So then, what do we get? what result do we get? We get kind of this kind of very cool result. So I'm going to write it out and then explain exactly what this means. So I'm going to write this out, f of r of t, r prime of t. So this is our good old-fashioned definition that we learned about last week. And the interesting part is what comes at the end. Maybe I'll put like an a to b here. And so this actually, no more integral symbol. This is just equal to f of r of b minus f of r of a. So a lot written down here. We are going to try to digest everything that I wrote down. So let's break this down. So in theory, right, what does this say? This says, and I'm going to deep dive into the details a little bit more, but let's look at what I wrote in the blue and the green. This says that if we have the integral of some conservative vector field, right, the gradient of f right here, this is a conservative vector field. This is some vector field f. Okay, and I rewrote that over here. Okay, if we try to evaluate it along some path C, so in the direction of our path, which we have parameterized in terms of r, if we try to evaluate this line integral, okay, which in its raw form is the process of doing this whole nonsense right here. Remember from our last video, that this is how you go about evaluating a line integral. It's basically it is the value of your vector field with respect to your path, and then dot, how do you get dr? Well, dr, there was a relationship between dr and ds, and we did it last time, and it turns out that dr is the same thing as this, which should make sense because dr dt times dt, this is the same thing as dr, which we had over here. And what is dr dt? Well, that right there is just r prime of t. So that's how those two connect. And what does it say? It basically says that instead of having to evaluate the line integral, instead of having to parameterize everything and figure out the vector field and figure out r prime and do the dot product and then integrate, we don't have to do any of that. It just simply says that we can just plug in kind of the endpoints to get our solution. Now, I want to talk about a couple things here, and I'll do a quick example. When we say C is a smooth curve, what we mean here is that it is differentiable. Okay, differentiable, why is that, why does that mean smooth? That's because if something's differentiable, it doesn't have any sharp points. Okay, you might remember that the absolute value of x is not differentiable because it has a sharp point at 0. So when we say smooth, we just mean differentiable. And even though it says smooth curve, right, we could be talking about some sort of curve that consists of a bunch of pieces, right? It can be piecewise smooth is what we call it. It could look something like this, and maybe it has its own little curve, I don't know, something like this. Oops. Okay. And the idea is if this thing represents our path C and each little section is piecewise smooth, if it's piecewise smooth like that, then we can go ahead and use this property. And the key thing here is that we have a conservative vector field. So for example, okay, let's just pull out of thin air a random vector field, or excuse me, a random potential function. Okay, let's make one. Let's keep this super simple and use x squared times y, okay? And so I'm going to create a gradient vector field. So because the gradient of f, which is going to be my vector field f of xy, has a p component of what? Well, if we're doing conservative vector field, then we take the partial with respect to x, we get 2xy. And then the second one, we take the partial derivative with respect to y, and we get x squared. So this right here, remember that's my p term, This right here is my Q term, so on and so forth. So this is a gradient vector field because I just randomly started with the potential function and came up with you know, the gradient vector field, so it's conservative. Hooray! Since it's conservative, we're on the right track. And let's let C be the first quarter of the unit circle. First quarter of the unit circle, oriented clockwise, or oriented positively. So counterclockwise, the way we normally use it. Let's keep things simple. Okay, so I haven't even asked us to do anything, but what we're going to do is I would like to evaluate. Okay, I would like you to evaluate the line integral of this vector field over this path. Okay, so find the total value. Remember, if this vector field represents heat or energy or probability or whatever, right, over this path, we're going to find the total heat, total energy, total probability, whatever it represents. If it's mass, it's total mass. If it's work, it's total work. Okay, and so in doing this, we have two options, and let me kind of draw a little sketch of what it is that we're doing over here. So we have our little quarter circle. Okay, we're oriented positively, something like this, and by now we know that a good parameterization for this quarter circle is going to be cosine of t and sine of t. Okay. And so we're evaluating this particular vector field over this curve. Okay, great. So how do we go about doing this? Well, option one is the old school way, okay? We know that t is going to go from 0 to pi over 2. How do I know that? Because with this particular parameterization, t equals 0 is here, and t equals pi over 2 is up at the top, because that's how the unit circle works. Our vector field f needs to get parameterized in terms of this curve, because we are looking at the x and y values that exist exactly on this curve, so no need to get tricky with it. So where's our vector field? Well, our vector field is the vector field 2xy comma x squared. And then we're going to need to replace all of these x's with cosine of t, and then all of the y's with sine of t. And then what are we missing? Well, we're missing the dot r prime of t, dt, right? This is our dr term. And r prime here is going to be, well, negative sine of t comma cosine of t, right? There's a lot of work that we already have to do, right? So let's keep doing it just to kind of drill in the point. So if we were doing this, right, integral from 0 to pi over 2, we're going to have our parameterized vector field, so 2 cosine of t sine of t comma sine squared of t dot negative sine of t comma cosine of t dt, right? And then from here we have to do the dot product, so we'll have integral 0 to pi over 2, and then we have to do the dot product, so it's going to be the first term times the first term, so we're going to get a negative 2 cosine of t sine squared of t, plus, what do we get when we do the second set of terms? We're going to get cosine of t sine squared of t dt. We can add these together, actually, it's nice, so we'll get a negative integral 0 to pi over 2 of cosine of t sine squared of t, and actually from here we can just do a quick u substitution to figure this thing out. So dot 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 u equals, you know, sine of t du is equal to cosine of t dt, and we can go ahead and finish it. So I'm going to just say you can finish this, put a star here. Okay, that's option one, lots of work. Okay, lots of work, but doable, right? We have a process. We logicked through our process last time. And again, I cannot urge you more to go back to last week's videos and make sure you completely understand where these formulas are coming from, because this week and next week, the formulas start coming, and they come fast and furiously and with no mercy. And if you do not understand the building blocks, you will not understand the larger formulas. So that was option one. Option one was we were given a vector field and we go through it the regular, just fully thought out. This is how you evaluate a line integral in a vector field over some path. Option two is we use the theorem. Now, why can we use this theorem? Let's look back at the conditions, okay? The conditions say that our curve has to be differentiable. Well, lucky for us, this is quite differentiable. You can take the derivative of cosine, take the derivative of sine, and over the values for t from 0 to pi over 2, we're not going to have any issues with continuity or differentiability or anything like that. So lucky for us, this is a differentiable curve. It's a smooth curve. Hooray. We have some values for t, and we already know that we have the gradient of f, right? F itself is differentiable. That's one of our other conditions. Clearly, this is differentiable, right? Derivative is, 2xy or x squared, and those have no problems. This vector field is clearly continuous on this curve because, again, no problems with 2xy and x squared. There's no holes, no gaps, no places where we're undefined. So, cool. This kind of small little checklist of things that if you're going to continue in the field of mathematics or you want to get a master's degree in the STEM field, you will have to kind of understand the whys of, why we're being so specific with all those conditions. But for now, we're more interested in using the end result, which basically says that the answer is as simple as plugging in the endpoints. You're like, wait, really? Well, let's take a look at what that means. So option two is that we can simply just evaluate f of r of the second endpoint minus f of r of the first endpoint. So what does that mean for us? Well, our f of x, right, or excuse me, our f of xy is equal to x squared y. Okay, now we need to first determine, the only things that we're really missing here is what is r of pi over 2. So let's figure out what that is. So r of pi over 2 is going to be, well, cosine of pi over 2 is 0, sine of pi over 2 is 1. And then we also need r of our first term, which is 0. Cosine of 0 is 1, and sine of 0 is 0. Okay. And so what does this mean? This simply means that we take our function and I'm going to, so let's do f of r of b first. I'm going to plug in 0 for x and 1 for y for the first one, because that's f of r of pi over 2 is simply going to equal 0. And then f of r of 0, well, that one is also going to equal 0, actually. Amazing. So it turns out that the answer here is just the difference between those two. It's the second one minus the first one. So the answer for this is 0. Boom. And we're done. Easy peasy. Didn't have to evaluate any integrals. Didn't have to worry about bounds. Didn't have to worry about r primes. Nothing like that. Okay, so this is a very useful little shortcut. And it only works, okay? I will put an asterisk here, okay? It only works for conservative vector fields. Okay, conservative vector fields. Okay, conservative vector fields. All right, so that's cool. Okay, so what else can we do with this theorem? Well, let's see. Let's draw a little axis and let's ask ourselves that question. What else can we do, right? If we have the starting point of some path, right, that happens when t is equal to a, and if we have the ending point of some path when t is equal to b, and let's say that in this in this space, right, we're dealing with a conservative vector field. So it has whatever special property is needed, that we are dealing with some conservative vector field f, that it is the gradient of some scalar function, little f, okay? And we said that what this theorem basically says is that if we have some path going, right, some path C, that is going from A to B, and we're trying to evaluate this line integral in the direction of that path, right? That basically all we need to do is to calculate, what do we get when we plug in the second endpoint, what do we get when we plug in the first endpoint, and we're done, right? That is it. And so you're like, okay, so what did we need to do in order to figure this out? The only thing we really need to figure this out is we need f, we need little f, which, I gave us in the last example, but, from last week's classes, if we're given a vector field and we think or we know it's conservative, I showed the process for how we could go about coming up with little f on our own, so that's not too bad. And then the second thing we need is we need our parameterization, right? We need r of t. Now let's really think about what this theorem said. It said if you have a conservative vector field going between 2 points, you have a curve going between it, the answer is the same as just plugging in the endpoint minus the initial point. Now, what if I had a different path? What if I had one like this? What if I have another path, I call it C2, and I want to evaluate the integral, okay, the line integral over the path of C2? Is the answer still this? Oops, and it should be B. All right, B minus f of r of a. Okay, is this still the answer? And the answer is yes, right? The answer is yes, because, the conditions of that theorem still hold. This is a conservative vector field. The path is smooth, no problems, okay? And so it turns out that I could pick a completely different path, and it turns out that one of the properties of a conservative vector field is that the answer is still going to be the exact same as if I took a more direct path. I could have taken a path going directly to that point, call it C3, and this would have still equaled the same exact line integral. It's a very nice property. Okay, so why is this nice? Why is this nice? Is this nice? Because if you have a line integral, and let's say I asked you to evaluate the line integral for C2, so I asked this one, okay? The parameterization for C2, my r of t here, could be really disgusting. It could be like negative 3t sine of 2t squared, comma, cosine of the natural log of t, right? It could be something super disgusting for that path because that path looks very terrible. But the path for C3, for instance, this path might just be a straight line. It could be something super simple, right? It could maybe be like 2t and t plus 1 or something like that, right? It could be something super duper simple, a nice straight line. And so when you have to pick and you're like, okay, well, I'd like to use the fundamental theorem of line integrals here because of all the properties that have been satisfied, you could choose any path that you want and you're going to get the same answer. So if I'm trying to use the fundamental theorem and I'm trying to evaluate, say, let's say I'm trying to do some vector field which maybe looks like x squared plus y, comma, y cubed minus x. Let's say that's my vector field dot dr. And I ask you to do it over C2. You could say, well, this is a conservative vector field, right? This one that I made is not conservative. This right here is not conservative, but I'm just doing this for illustrative purposes. If we have some vector field f, you could say, hey, look, this path sucks. And if I want to use this this end result, I would have to figure out what that path is and then plug it into my potential function f. So why don't I just ixnay this? Why don't I just draw an x through it? And why don't I just draw a different path going straight between the points, use this nice simple parameterization, and solve it using that one? And the answer is you can absolutely do that. Okay, so that's really nice. So we call this property independence of path. Okay, so this property of a conservative vector field that you can pick any path that you want to go between 2 points and still get the same answer kind of lends itself to thinking why this might be a conservative vector field, right? You might think of if you're driving a car and you go up a steep hill and then go down and you end up right here, are you going to use more or less gas than if you had taken a different road that was just only uphill the entire time, right? So the first one went uphill and then down. You got to cruise a little bit at the end. And the second one, you don't get to cruise at all, but your slope is not as steep the entire time. And it turns out that you'll use the exact same amount of gas, all things considered, if this is a conservative vector field. And lucky for us, we kind of live in a world where energy is conserved. So most of the calculations that we're going to do deal with conservative vector fields, so we get to use this really nice property. Okay, so I think that's going to do it for this video. This kind of covers just an introduction to the fundamental theorem of line integrals. It introduces the concept independence of path, and it talks about kind of like the power of doing this. Maybe one more thing to note as to why this might be super useful to do is because if I give you a path and I say, all right, there's my starting point, and I say that, I want you to calculate the line integral. I want you to evaluate the line integral over this path here. Okay, so this is my path C. Consists of 3 smaller parts, C1, C2, C3. They're both piecewise. They're all piecewise smooth, and that's really nice, so no issues there. And I want you to evaluate the line integral of some vector field f dr over my path C. Well, you could do it. You could break this up into 3 pieces. You could do a line integral over C1. You could do a line integral over C2, and you could do a line integral over C3. You could do it 3 separate times. Hooray. Or you use the fundamental theorem and you figure out, okay, if this is a conservative vector field, so it's the gradient of some scalar function f, you figure out what f is, you figure out what your f is, and as soon as you have that, the last thing that you need to do is, well, to do what? Well, you can either work with all these pieces, or I can use the conservative or the fundamental theorem of line integrals, the fact that this is conservative. I can draw another little path here, call it C4. And this is, again, a nice straight line. I can come up with some parameterization for that. Okay, it's going to have its own little parameterization. And all I have to do is remember the whole point of independence of path, the whole point of this theorem is that I don't have to do all of these 3 calculations. I can simply just say, so if I'm going between some starting point and some ending point, it doesn't matter what path I take to get there. I can take this long path that consists of the yellow, the green, and the pink, right? C1, C2, C3, or I could draw my own path, like a straight line there, and I could simply just say this is just the integral over C4. And so instead of doing 3 separate integrals, I just do 1 single integral, right? I just come up with my own little path directly between those 2 points, and I can use the fundamental theorem where I just kind of plug in the endpoints and subtract, and I'm going to get the answer. So that's a really nice property. This also comes with one more property, which is if I have some path that starts here, and it goes on its merry little journey and then comes back to where it started, what do you think the value of this particular line integral is going to equal? Well, if this is a conservative vector field, and we have this path C, then we still get to use the fundamental theorem of line integrals, so r of b minus f of r of a. But what special property does a and b have this time around? Well, what's my starting t value and what's my ending t value, right? Well, they're the same, right? This is t equals a, and if I'm ending at the same point, this is t equals b. So what does this line integral represent? Or what does it equal, excuse me? Well, it's just going to equal 0, okay? And so there's a nice property that says the line integral, or the closed line integral of a conservative vector field is equal to 0. Which should make sense, right? If we think about this as an energy field, right? If we think about this as energy, right? If I go up a hill and I come down and I were to just go one way, I would expend energy and I'd gain some energy back because I'd be pedaling up and then I'd be relaxing on the way down. And in theory, mathematically speaking, the total amount of work that I would have done would be 0. And you can imagine just if I go and do some work going this way, and then I get some work back going this way, and I get some more back going this way, and maybe I lose some going this way, right? Eventually, it all kind of averages out, and we end up getting 0. And so the notation for a closed line integral is a line integral like this, but it has this little loop. Right in the middle of it that basically indicates this is a closed line integral. So this always equals 0 for conservative vector fields only, okay? For conservative vector fields. Vector fields only, okay? Really nice property, saves you a bunch of work, and could be useful for any upcoming homework or quizzes. And in the next video, we're going to cover the more interesting case, which is, what if our vector field is not conservative, right? Do we still have this property? Because this is a really nice property. Do we still get to use the fundamental theorem of line integrals? Do we still just get to subtract the endpoints? That's something we're going to investigate next.